Thanks to IDD for hosting this event to get information out about drill bits. So today I'll be talking a little bit about how we've utilized high-speed data at the bit from the sensor that Lynn Laban had talked about earlier, our weight on bit and torque on bit. Okay, so a quick overview. We'll go through a little bit of background on the application, the bit, get into the high-speed data or get into the downhole data analysis, and then talk about what we did to improve operations. So what I'll be talking about today is a dedicated curve in Midland County that was targeting a Wolfcamp A. The goal here was to identify why the bit or why the system was losing toolface control. So we did employ our cerebro force so we could measure downhole weight and torque on the bit. And here's kind of a brief run summary. It was a dedicated curve, drilled it in about 16 hours. It was a 6.5 inch, 7/8, 5-stage, 0.29 RPG motor with a 2.38 degree bend. You can see the dole condition. We built from about 0.7 degrees to 92.2 degrees, and the bit came out in very good condition. It was graded a 0.1 and had a chipped cutter on the lower shoulder gauge area. So hopping into the data, I just want to kind of give everybody a background on what we'll be looking at, kind of set the stage for the next few slides. So the top graph is going to be weight on bit. And here we're comparing surface weight on bit in blue to the downhole measured weight on bit in red. And you can see that after we hit roughly 30 degrees of inclination, the downhole weight stays the same while the surface weight increases quite drastically. This is due to that BHA laying in the hole, and there's more friction to overcome from your surface weight. Now the bottom graph is our torque on bit. We have surface torque in blue and then our downhole torque in red. Now for most of this run we were sliding, so you can see from roughly 8,500 foot to about 92.75 we were sliding. So top drive torque, top drive's essentially locked, you don't get any measurements. However, the first stand was rotated and then they rotated out a little bit at the last stand. You can see here when we started rotating that the surface weight on bit and downhole surface torque on bit and downhole torque on bit were relatively similar. They did have a tangent uphole in their 12 1/4 section, and so there was a little bit of friction in that drill string. By the time we finished the curve, we have a very large gap between surface torque and downhole torque. Again, primarily because that BHA and that drill pipe are now sitting in a curved assembly, garnering much more friction. Okay, so getting into toolface and what the heck goes on downhole when we lose toolface control. On the top graph, we're looking at the downhole torque on bit, so specifically what the bit was seeing. In the middle is downhole bend on bit, or the side force that the bit was seeing, and then on the bottom is our toolface measurements. The blue is going to be our gravity toolface, and then the green will be the mag. And all of the black lines indicate inclination. So the first thing that pops out here, and we're looking at 1 second data to kind of put everybody on reference, is how that first roughly 30 degrees has a lot of spikes or swings in both toolface control and bend on bit and torque on bit, which makes a lot of sense because if you're sliding, you should be drilling a relatively gauge hole. As soon as you lose toolface, that bit wants to spin around on that bend of the motor and open the hole. Well, the only way to open that hole is to take an extremely large side force and torque to make that happen. And so we're going to investigate what's going on there. So here's a little bit of a snapshot where we zoom in, and it's pretty dang clear that just about every time we lose toolface, here in blue, we see a spike in bend on bit. You see it here, here, here. It's pretty constant throughout the run. However, when we get to the end of the run, when inclination is over 60-ish degrees in this case. Our bend on bit is pretty dang smooth, and our tool face control is pretty smooth as well. So there's friction in the hole that is helping us maintain some of that stability. All right, so now we're going to jump into roughly 5 foot, 6 foot of drilling. So again, I'm going to set the stage here so everybody can read the graphs. The top one, red, is downhole weight on bit, blue is surface weight on bit. The middle chart is tool face gravity, and then the bottom chart is differential pressure. So you can see that at roughly 26 or 86, 24, we start to see tool face creep up, creep up, creep up, and then we flip by about 180 degrees from where we started. But why? Well, on this top graph, we're looking at the surface weight on bit stays pretty constant. We see a little blip here, a little blip here, but we're talking maybe 1,000 pounds most variation for surface weight on bit. But the downhole weight on bit is a completely different story. We're tracking pretty well about 2,000-ish pounds, 4,000-ish pounds off from surface weight on bit, and then within about a second, because we're looking at 1 second data here, within a second we lose about 50% of weight on bit downhole. But you would never realize that from your surface weight on bit because it stays constant. So as soon as you lose that surface weight on bit, lo and behold, your differential starts to drop off. So essentially what's happening is the bit starts drilling off. And as the bit starts drilling off, we lose depth of cut, we lose torque. And if you're drilling with wraps in your string, all of a sudden those wraps start to come undone and it wants to flip your tool face on your bit. And that's essentially exactly what happens. As differential drops, we lose torque in the system, tool face flips, and then when weight on bit does come back, about a foot to a foot and a half later, differential comes back, and we get back onto a good, solid tool face again. Now, the big question here is why? So what would cause this? Is it the bit design? Unlikely, because we don't see, it's exactly a weight on bit issue. If you put less weight on bit, you're going to get less torque, you're going to get less depth of cut. Is it an operating parameters issue? Again, unlikely, because surface weight on bit and surface RPM in this scenario has not changed. So we believe what happened is that somewhere in this system, whether it was in the BHA or a tool joint, we had friction. We hung up momentarily, which caused weight on bit to no longer transfer to the bit. And things kind of went haywire. So what are we going to do about it? We felt pretty confident that this was a true weight on bit and friction related issue. So we discussed with the operator about adding in a friction breaking tool to their string, to their assembly. So we put basically an agitator in the string. Then we ran same assembly, or pretty close to the same assembly, with that friction measuring tool, friction breaking tool, again with Cerebro Force, to see what happened. So here was the follow-up run. We drilled another dedicated curve. This one was a Wolfcamp B target. We saw a little bit reduction in hours and a little bit higher ROP. Unfortunately, the tool face data did not record in the EDR system, but because of our first run, we know that spikes in both bend on bit and torque on bit are a very, very good proxy for loss in tool face control. And so in run one, you can see we had quite a few issues in torque and bend throughout that first 30 degrees or so. In run number two, we saw significantly reduced spikes. So we didn't eliminate the problem completely as far as tool face control, but we did significantly reduce it. Furthermore, when we went and looked at the data in more granularity, we no longer saw this issue. Yes, we had other tool face issues, but it was not due to a lack of weight on bit transfer. It was due to more traditional stick slip, where we saw both torque and weight increasing, and then the bit stalling, losing tool face, having to pick up and reorient. So just to kind of conclude this, we successfully used cerebro force to measure downhole weight, torque, and bend, and identify a root cause of why we were losing tool face control. We were able to implement some modifications to the BHA to mitigate that root cause and perform better on the next run. Now, there were, as I stated earlier, 2 other causes in loss of tool face control, and Lynn kind of touched on this in some of his data with the weight on bit increasing prior to torque or torque increasing prior to weight. We believe that some of those can be addressed with bit design, and that the other one needs a little bit more further analysis to truly understand why that's occurring. So as far as what's next, Lynn I never realized this, but every hour we're capturing 72 million data points. So I guess I've read over 8 million books tenfold since I've been in the Permian team looking at high-speed data and downhole data. But our goal is to use this data to improve bit design. But there's more uses than that. We're also examining this data to improve both operating parameters, and as you've seen in this presentation, we're also utilizing it to improve the drilling system. Whether it is BHA design or adding additional tools, we can gain insights from our downhole data to better perform, to increase efficiency of the drilling operations. So that's what I had on today's session. If you have questions, feel free. There is one advantage of going late in the day and being virtual, and so I'd like to thank Mitch for his presentation on stick slip at the bit. And it is something that we are seeing more and more with the downhole data that we capture. So bringing it to light in a forum like this, I think, is excellent. And I did want to just kind of validate Mitch's point that this is an issue, BHA-induced stick slip. And here is just a snapshot of high-speed data kind of enforcing or reinforcing what Mitch had shown. What you can kind of see here is pumps come on, and we're looking at RPM, high-speed data at the bit. Our bit spins up to roughly 120 RPM. When the top drive kicks on, we start seeing this oscillation. When we tag bottom, we're still seeing that same oscillation. But as we oscillate, which is stick slip by any calculation, we never drop below motor RPG. So the motor is always spinning at the full 120 hertz. The BHA stalls, releases, stalls, releases. So it is a concern. To Mitch's point, it doesn't necessarily affect the bit as much as a complete stall, but it is something that I think the industry needs to analyze a bit further and truly understand why this occurs. So that's all I've got for today. Thanks, guys.
Thank you, Seth. We appreciate it. We're going to open up to questions. Any questions here in the room? Y'all are killing me. It's after lunch. We fed you. I would think that you can come up with at least one question. All right. Seth, I have a question for you. And this may have been covered earlier, but this is really for me to get a question out there to kind of start this process going. But how is the data delivered to the customer typically from your technology?
So the graph that I'm showing right here is from Spotfire. So to Lynn's point, we produce a standard report that condenses the data down to 1 second intervals. So we do some averaging, we do some max-min calculations. We put it into Spotfire and we look for triggers. We look for spikes in dysfunction. We look for changes in relationship to calculated RPM and downhole RPM. Then we go start digging into the 1 second details, and if needed, we'll dig into the 1,000 hertz data. That is then analyzed by the local team in the Permian. So it is a group of engineers, application engineers, and myself that review it. We make our own conclusions and assumptions, and then we discuss with the operator. If needed, we do have resources back at the research and development team that can help us out, especially dealing with the high-speed data. But the goal is that this knowledge and learning is transferred to the local teams and not held in a silo at the corporate offices.
Perfect. Do they have access to the raw data?
Yes, everybody has access to the raw data. I'm not a physics major. I think James had commented earlier that you kind of need a physics degree to deal with some of this raw data. So the raw data, I'm not going to say is our forte in operations, but we know how to analyze the 1 second and then ask for assistance if needed on the raw 1000 hertz information.
Okay. Let's see.
Mark May had asked a question about what types of PHA adjustment may help mitigate some PHA system.
Okay. So Mark had a question for you, Seth. Mark May.
Okay.
What was the question?
I was unable to hear it.
What changes to the VHA did you make to help mitigate the stick slip?
Yes.
Okay, so what changes did we make? The primary change was adding an agitator into the system, and it wasn't really stick slip per se that we were trying to solve. It was a loss of weight on bit transfer while drilling or while sliding. So the only change to the BHAs in these two runs was the motor size went from a 6.5 to 6 3/4, and then we added an agitator into that system.
Seth, Blaine, come on here. I'm going to ask you the obvious question. How long was the gauge length on the drill bit?
Oh, Blaine, I knew you were going to say that as soon as I heard your name. In this application, we were running a 3-inch gauge pad.
There you go.
Thank you for the awesome question, Blaine. All right. Thank you, Seth. We appreciate it. If we don't have any other questions.